Hey everyone, welcome to another episode of the Blaspheming Bite. Today we're going to do another problem from Recursion, and it's called the Sudoku solver. And the problem is basically you're given a grid, a Sudoku question, and you're tasked with finding out the solution to Sudoku. Now you can Google up what Sudoku is, how it works, but the general idea is you are given a 9 by 9 block, and then within those 9 by 9 blocks you're given another 9 by 9 block, and you need to fill in numbers from 1 to 9. Now the constraints are that you're not allowed to have any numbers repeating within each block. Also, you're not allowed to have the number repeating in that row or in that column. So it's a game, it's a very fun game to play. The different levels, like easy, medium, hard, and it's really addictive game if you get into it. But anyway, that's not our problem. Our problem is to solve it using the computer, because why would a human do it unless he's really tired or bored and he's got nothing else to do in his life, right? But let's actually try to solve this. Now, if you notice, how do you think you're going to come up with a solution for this? So you're given a Sudoku grid, right? And then you need to fill in everybody. Let's say that I need to fill in something here. Okay, this is an empty spot. Okay, you're given something like this. Okay, and then you want to find out what you need to be able to put here and here. Okay, now if you look at the grid, you can find out that in the smaller grid you can find out the two things that are missing are 2 and 9, right? Are 2 and 9. Now we could think, okay, let's use 2 here, right? And then you check, okay, is there anything for 2 here? Is there anything for 2 here? If there's not, you can put it there. And then naturally you would think, okay, I can put a 9 there. So what did we do right there? We pre-computed a value, put it there, and then we checked whether we can put that, whether we can use that there. Now, is that really required? Like, did we have to find out what are the remaining values that we could find? No, not really. There's really no benefit to doing that. But instead, what we'll be doing is we're going to take all of the values, put it in there, see if it violates our principles or our constraints, and then we keep moving forward. If it doesn't violate, great, let's keep going down the recursive stack. Now, why do you think this is a recursive call? If you've noticed, every time you have a value or you've arrived upon a value, you need to add that value to the position in the grid, and then take the whole grid and give it your recursive function, right? Because every time you go down, like let's say you had 64 slots which are empty, and now you have found one and you have made it 63 slots. Okay, you need to put all of that information into the recursive function. Like this whole grid has to go into the recursive function. Just the thing that keeps moving, varying, is where you are at right now in the grid, right? So to make our life simple, we're going to reduce we're going to abstract out some functions. Okay, so every time you're going through the grid, okay, so you come here, when you see that there's nothing there, then what do? You move on to the next one, and then you come here, there's something is there, and then you come here and you notice that okay, there's nothing there. What are your possible values? You can go all values from 1 to 9, right? So when you're checking from 1 to 9, let's start with 1. Okay, we're going to check if 1 is a valid number. We're going to call another function called is valid, where what are we going to pass? We're going to pass in the grid, right? We are going to pass in the value that we want, and what else? We are also going to pass in the index. Now I'll tell you why. I mean, it's quite obvious why the index is important, right? Now within is valid, we're going to check 3 things. Is valid in row, is valid in column, and is valid in your subgrid. Okay, now if all of these functions are satisfied, and then so this guy will return a boolean. He will say, okay, yeah, it's valid. You can keep going down the tray and down the stack. And now, why do you think we need the I and j values, right? How do you know what row you're at? Okay, so if you want to check for is valid row, you're going to keep I constant and move the j values, like check for every other position and see if your value matches that value. If it not, you will immediately return false and go back. Similarly, when you're doing is valid column, you're going to do you're going to keep j constant and then keep moving the I, and then finally is valid subgrid. Now this is something interesting that we can look into. I'm going to define this is valid subgrid. Let's look at that. So in is valid subgrid, we're going to check whether within a particular subgrid are those values valid. Okay, now in order to be able to do this, we need to go through each and every element in that subgrid. For that, the example solution that's there has a neat trick, and the trick is wherever you are, it doesn't matter. We are going to reset our counter to start at the beginning of that subgrid. So for example, your point was over here. You're going to move it here, and then you're going to iterate through all of these guys. Okay, now let's do an example. Let's assume that we have to check what value needs to come here. Okay, again, somebody now tell me what's the position of that. So that'll be 0, 1, 2. So yeah, so the row would be 0, 1, 2, and the column number is 0, 1, 2, 3, 4, 5. Okay, now if you want to reset this guy to this position, how can we do that? Look at this. Just divided by 3, which is the size of the subgrid. Okay, so you get 0 and you get 1. So the row would be 0 and the column would be 1. Check this out. Let us multiply this value by 3. What are we going to do? We're going to get 0 and 3. Okay, now navigate to this position. So the row number is 0. Okay, that's fine. We are here, and then the column is 0, 1, 2, 3. So what did we do there? We were able to reset our pointer to the position where the subgrade starts. Okay, and then because I've explained this, now it'll be easier for you to look at the code and see how we actually iterate through these guys. So when you're doing a nested for I equal to 0, 2, 3, 4, j equal to 0, 2, 3, you're going to check the value of grid as k into 3 plus I, sorry, not k, or whatever you got here. So I'm going to call that as row and column into 3 plus j. So by using this, you compare it to the value and you will basically iterate through every element in that. So using that is valid subgrade. You can find out if a particular value is in a subgrade or not. Okay. There's another way of doing this iteration through the list, and maybe not useful here, but you can use it somewhere else. So assume that you're given an n by n grid. Let's just have 3 by 3 grid. Do you need two variables to be able to find out where you are in the grid? Not really. If, let's say, we're going to name the positions as 0, 1, 2, 3, 4, 5, 6, 7, 8. Alright? If I'm giving you a value 7, how do you find out where you are? So to find the row number, you would do 7 divided by 3, which is 2. So you know that you are at 0, 1, 2. You're here. You know you're here. And if you do 7 modulus 3, you get 1, and then you get the column number. So that's a really neat trick to go through a table without really having an x and y. You just need one. But you need to have the upper bounds. It doesn't have to be 3 by 3, it could be 3 by 4. The only difference would be you would be moduloing you'd be modulating by a different number here. Okay, that's the only difference. Okay, coming back to our real question. Assuming that you have a way to iterate through all of the elements, and it's pretty straightforward. You can look at the solution. Assuming you have that, you're iterating through everything, and whenever you iterate, if you have a valid value, right? You put in a value, you sent it through all of those, is valid row, is valid column, is valid subgrade, and came back true. What do? You're going to keep going down the recursion. Okay, you're going to do the helper function, and you're going to send the grid, and you're going to increment your row number. Okay, so you're going to assume that you're going like this. So you'll do a row plus 1, your column stays the same. Okay, and if that's also true, then you will return true. What this basically means that you have a value that was valid, you plugged in that value, you sent the new grid into the recursive tree, and then at some point he reached the very end, and then he gave back a true. Okay, so that means that that you found the solution. Now, if it's not a valid solution, what are we going to do? Remember that value that we set into the grid, we are going to unset it. So we would do an unset of the value, and then we would return, and then we would keep going through, and then we would return false. So what does that mean? If you're returning false, it means that this function would have failed, and then it will not go down the recursive stack. That means that whatever value you selected is wrong, so keep going back. Finally, let's just see when this is going to terminate. When do you think this would terminate? You keep going, you keep going, you keep going, you keep going. And finally, if your row is equal to 9 and your column is also equal to 9, that basically means that your row has come all the way down here and your column has moved all the way down here, which means that you have reached this position. The moment you reach that position, that means you made it, man. You're at the end of the tunnel and you have the solution to the Sudoku flying out in the air, and that's just fucking amazing. I had this question asked to me for an interview, and I was not able to come up with a solution, but we gradually reached there. So I highly recommend this question. It's pretty interesting. I think you should all watch it. You should all learn it. Talking about the time complexity, you really don't know how far or how long this is going to take, right? At the best case, you could say this is exponential time, because it could go all the way down, keep coming back, go down, keep coming back. It's really it's something you call an NP complete problem, and there's no meaning to saying what is the time complexity for this question. Anyway, that's a Sudoku solver. I hope you guys had fun learning this with me. It was really fun for me learning it. Hope you enjoyed, and have a nice day. Hey everyone, if you like the video, please make sure to like, subscribe and share. There's also a GoFundMe page where you can go and fund my wife's dental school, and I would like it if you would donate anything. $1 would be fine. Thank you.